The images came in late, one observing night, deep exposures from coordinated telescopes, stacked frame by frame to coax faint structure from the darkness. Astronomers leaned closer to their monitors. There, jutting from the nucleus of 3I Atlas, the third confirmed visitor from another star system, was something that defied every instinct trained by decades of comet observations. A narrow, ghostly spike, a tail-like feature. But it wasn't streaming away from the sun, swept back by radiation and solar wind like every other cometary tail ever documented. It was pointing toward the sun, not away, toward. That shouldn't be possible. Comet tails are pushed outward, always outward, by the relentless pressure of sunlight on dust grains and the drag of solar wind on ionized gas. They flow anti-sunward, away from the star, tracing elegant arcs that point into the emptiness beyond. It's one of the first rules written into astronomy textbooks, confirmed by centuries of careful observation, encoded into the physics we teach undergraduates. Yet here, in front of a dozen independent observers scattered across 3 continents, was a structure that appeared to violate that rule. An extension aimed in the wrong direction. As if the forces had reversed. As if geometry itself had turned inside out. The confusion didn't arrive as panic. Astronomers are trained to distrust surprise, but as careful, methodical questioning. Could it be a projection effect? A thin sheet of dust seen edge-on, compressed by perspective into a misleading spike? A trick of viewing geometry, where the same photons encode multiple possible, 3-dimensional structures depending on what you assume about orientation. Because this is the uncomfortable truth of astronomy. The same image can tell different stories. The same set of scattered light can be interpreted in contradictory ways, and certainty emerges only after eliminating every alternative explanation, one patient layer at a time. This is not a story about broken physics. This is a story about how easily appearances deceive, even trained observers, even in the cleanest data. A sunward-pointing tail, an anti-tail in the careful language of the field, can exist without violating a single physical law. But understanding why it exists, how it forms, and what it reveals about the object that made it requires unraveling dust dynamics, radiation pressure, orbital mechanics, and the subtle geometry of perspective. The anti-tail phenomenon is rare but real, documented in a handful of comets under specific alignments. When Earth crosses near the orbital plane and weeks-old dust drifting along that plane suddenly snaps into view as a compressed line, a spike that can appear to aim anywhere on the sky depending on the observer's vantage point. But knowing such things can happen doesn't solve the mystery. It only sharpens the question. Not is this possible, but what arrangement of dust, light, and perspective could create this exact illusion, for this exact object, at this exact moment? The feature didn't appear in earlier observations. Frames taken weeks before showed the nucleus, perhaps a faint diffuse coma, but no linear extension. Then, within a narrow observing window, the spike materialized, faint, narrow, unmistakable. Independent teams processed the data separately, using different reduction pipelines, different sky subtraction algorithms, different methods to remove star trails, and correct for field gradients. Faint structures are fragile. Over-aggressive background subtraction can erase real signal. Gradient mismatches can manufacture false features. Imperfect star removal can leave linear artifacts that mimic jets. So the first step is always skepticism. Test the mundane explanations. Eliminate the processing ghosts. Rule out the instrumental errors before entertaining the extraordinary. But this time, the feature survived. Multiple observers, working independently with separate datasets, reported the same geometry, a narrow extension at approximately the same position angle relative to the nucleus, reproducible across nights, consistent in morphology. That reproducibility matters. It transforms the spike from possible artifact into structure, demanding explanation. The anti-tail is real. It exists in the data with enough coherence that dismissing it becomes harder than accepting it. Yet it remains delicate, hovering at the edge of detectability, faint enough that interpreting its nature requires assumptions about dust grain size, emission timing, and 3-dimensional orientation that cannot be confirmed from a single set of images. If you enjoy this unfolding mystery, subscribe for more Beyond the Solar Veil cosmic documentaries. The anti-tail didn't appear in every observation. Earlier images, taken weeks before, show the nucleus and perhaps a faint, diffuse coma, but no distinct linear feature. Then, within a specific observing window, the spike becomes visible. And in later frames, taken after Earth's viewing geometry has shifted further, the feature fades or changes orientation. That temporal behavior matters because it suggests the anti-tail is not a permanent structure, but a situational alignment, a configuration that becomes visible only when the observer's line of sight intersects a particular plane of material at a particular angle. Genuine outflow from a comet, gas and dust actively being expelled by solar heating, should evolve smoothly with heliocentric distance, growing stronger near perihelion and weakening as the object recedes. But an anti-tail behaves differently. It can appear suddenly, not because new material is being released, but because old material, dust ejected days or weeks earlier, becomes visible when Earth crosses into the plane where that dust is concentrated. The sky didn't change. The dust didn't change. What changed was our angle of view, and that change revealed a hidden structure at exactly the moment it looked most wrong. This is where geometry becomes the key to unlocking the paradox. An anti-tail is typically not a physical stream pointing sunward. It's a projection effect, a thin sheet of dust particles, spread along or near the object's orbital plane, seen edge-on. Imagine a flat disk of dust, tilted at some angle relative to your line of sight. If you view it face-on, it appears as a diffuse cloud. But if you view it edge-on, the thickness of the sheet compresses into a narrow line, and all the scattered light from grains at different distances along that plane piles up into a bright spike. That spike can appear to point in any direction on the sky, depending on the geometry, including toward the sun, even though every individual dust grain within that sheet is still being pushed anti-sunward by radiation pressure. The direction is a sky plane illusion, not a force vector. It's an artifact of perspective, not a reversal of physics. And once that realization settles in, the anti-tail transforms from a mystery into a diagnostic tool. Because if a narrow, sunward-looking spike exists, it tells us that dust is concentrated near the orbital plane, that the grains were likely released over a relatively short time window, and that the geometry between Earth, the object, and the sun has aligned in a way that makes that plane visible as a compressed line. But why would dust concentrate so tightly near the orbital plane? Why wouldn't it disperse into a broader, more diffuse cloud as radiation pressure and the slight gravitational influence of the sun and object act over time? The answer lies in the physics of dust sorting. Radiation pressure accelerates small grains more strongly than large ones. A micrometer-sized particle feels a stronger push relative to its mass than a millimeter-sized chunk. Over time, this sorts the dust by size. The smallest grains are blown into wide curved fans that sweep far from the orbital path, while larger grains, those massive enough that radiation pressure is weaker relative to their inertia, lag closer to the trajectory the object itself follows. If the anti-tail is narrow and well-defined, it implies the dust population is either dominated by larger grains, or the material was released in a brief burst that hasn't had time to disperse significantly. That constrains the history. A steady, continuous dust release over weeks would produce a broader structure. A short, outgassing pulse, perhaps triggered by a sudden exposure of fresh ice, a surface fracture, or rotation-driven jet becoming active and then shutting down, could produce a thin sheet. Fragmentation is another possibility. If the nucleus shed a small fragment, that event could release a localized cloud of dust that subsequently flattens into the orbital plane under the combined influence of the object's weak gravity and solar radiation. Each interpretation implies a different past for 3i Atlas, a different sequence of events we cannot observe directly, but can only infer through the geometry and brightness of the dust it left behind. The anti-tail becomes a fossil record encoded in scattered sunlight, and the question shifts from what is it to what does it remember? If the dust was released near perihelion, when solar heating was strongest, it would have had weeks to spread. If it was released more recently, closer to the current epoch, the sheet should be narrower, less dispersed. The morphology, the brightness gradient along the spike, and the rate at which the feature fades as viewing geometry changes all carry information about emission timing and grain size distribution. But extracting that information requires models, radiative transfer calculations, particle dynamic simulations, assumptions about dust composition and reflectivity. And those models are only as good as the data they're calibrated against. For a unique interstellar object observed over a limited arc with uncertain activity history, the uncertainties compound quickly. There's another layer to the investigation, one that introduces a split in the evidence. Broadband imaging, using wide filters that collect light across a broad range of wavelengths, shows the anti-tail clearly. It's a dust-friendly observing mode, sensitive to the continuum scattering of sunlight off solid particles. But narrowband filters, designed to isolate specific emission lines like those from cyanogen, diatomic carbon, or hydroxyl radicals, may show a different story. If the anti-tail is prominent in continuum light, but weak or absent in gas emission diagnostics, that strengthens the case for a dust sheet projection, rather than an ion tail driven by plasma interactions with the solar wind. Ion tails, when they occur, are often visible in narrowband images targeting molecular emission, and their morphology is controlled by magnetic fields and the speed of the solar wind, not just radiation pressure. The fact that the anti-tail appears strongest in dust-sensitive bands suggests composition and mechanism. But if there's a subtle color signature, if the scattered light is slightly bluer or redder than expected, that becomes a clue to grain size. Smaller particles scatter blue light more efficiently through Rayleigh scattering, while larger particles produce more neutral or reddened scattering. Color photometry, if available, can constrain the population. Yet the investigation cannot rest entirely on dust. The solar wind is not uniform, and the interplanetary magnetic field threaded through it can organize plasma into filaments, kinks, and sudden directional changes that complicate tail morphology. In certain heliospheric conditions, when an object crosses a current sheet, or when solar wind speed varies abruptly, plasma tails can exhibit complex, sometimes counterintuitive structures that don't align neatly with the anti-sunward direction. These are not common, and they typically require active gas emission to create a detectable ion tail, but they remain within the realm of known physics. The possibility exists that what appears as a dust anti-tail could have a hybrid origin, a dust sheet providing the narrow spike, with subtle plasma interactions adding curvature, brightness modulation, or fading behavior that pure dust dynamics wouldn't predict. Distinguishing between these requires multi-band photometry, polarization measurements to test for scattering geometry, and ideally spectroscopy to confirm or rule out gas emission. In the absence of that full suite of data, the interpretation remains layered, plausible mechanisms stacked on top of one another, each consistent with part of the evidence, none definitively confirmed. Looking forward, the anti-tail offers a unique observational target for future studies, but the window is narrow. As 3I, Atlas continues outbound on its hyperbolic trajectory, the geometry that made the anti-tail visible will shift. Earth will move out of alignment with the dust sheet's plane, and the compressed spike will fade, not because the dust disappears, but because the viewing angle no longer compresses it into a detectable line. Within weeks, the feature may be gone from new images, and the object itself will dim further as distance increases. Follow-up observations are constrained by fading magnitude and the need for large aperture telescopes with sensitive detectors. The Vera C. Rubin Observatory, once fully operational, will detect future interstellar visitors earlier and with higher cadence, potentially catching anti-tail events during their brief visibility windows and building statistics on how common such features are among small bodies crossing the inner solar system. The James Webb Space Telescope, with its infrared capabilities, might detect thermal emission from dust grains even when scattered visible light has faded, offering complementary data on grain temperature and size. But for 3A Atlas specifically, the anti-tail may be one of the last detailed structural features we can study before the object fades entirely from observational reach. What remains is not a a solved mystery, but a clarified one. The anti-tail is not a violation of physics. It's a demonstration of how perspective, three-dimensional structure, and the limitations of two-dimensional imaging conspire to create appearances that challenge intuition. A tail that seems to point sunward is almost certainly obeying the same forces that push all cometary tails anti-sunward: radiation pressure, solar wind drag, gravitational dynamics, but arranged in such a way that the projection onto the sky plane creates an illusion. The dust grains are still moving away from the sun. The sheet is still flattened along the orbital plane. The scattered light is still following the laws of optics and scattering theory. What's deceptive is the geometry. What's difficult is translating a two-dimensional image back into the three-dimensional reality it represents. And that difficulty is not a failure of observation. It's a fundamental constraint of astronomy. We see the universe from one point of view, at one moment in time, and we build knowledge by triangulating across multiple observations, multiple wavelengths, and multiple epochs to reconstruct what's really there. The anti-tail also serves as a reminder that interstellar visitors carry unfamiliar histories. 3I. Atlas formed in another star system, orbited under different stellar conditions, and spent an unknown length of time crossing the cold, empty space between stars. Its surface composition, volatile content, and structural integrity were shaped by processes we can only infer. When it encountered our sun and began to heat, it responded in ways that may differ subtly or dramatically from the solar system comets we've studied for centuries. An anti-tail appearing on an interstellar object is not unprecedented in principle, but it's a data point in a sample size that remains vanishingly small. Every feature, every anomaly, every unexpected structure contributes to the slow, patient work of understanding what normal looks like for objects from elsewhere. We don't yet know if 3I Atlas is typical of interstellar comets or an outlier. We don't know if its dust production history, rotation state, and structural fragility are representative or unique. We're building a catalog from individual cases, and each case teaches us something about the diversity of small bodies beyond our stellar neighborhood. The anti-tail, in this sense, is not just a curiosity. It's a window into processes that are difficult to study any other way. Dust sheets and orbital plane concentrations exist around many comets, but they're often invisible because the viewing geometry is unfavorable, or the dust is too faint. When an anti-tail appears, it's because the geometry has aligned, brightly, fortuitously, to reveal a structure that was always there but hidden. That alignment is rare, fragile, and temporary. It requires the object, the Earth, and the Sun to occupy specific positions at a specific time. Miss that window, and the structure vanishes back into invisibility, not because it ceased to exist, but because the perspective changed. Astronomy is full of such moments, phenomena that exist at the edge of detectability, visible only when conditions conspire in the observer's favor. The anti-tail is one of those moments, and the fact that it appeared at all, that it was noticed and documented and analyzed, is a testament to the care and persistence of observers who know that faint, transient features often carry the most information. In the end, the sunward arrow doesn't point at the sun. It points back at us, at our assumptions, our viewing angle, our need to remember that space is three-dimensional and certainty is often illusory. The anti-tail of 3I Atlas is a quiet lesson in the limits of seeing, a reminder that what looks simple on a flat image can encode complexity that takes patient analysis to unravel. The dust is there. The physics is understood. The mystery is not whether such things can happen, but why they happen this way, at this time, for this object. And the most honest answer, the one that respects both the data and the uncertainty, is that we've narrowed the possibilities but not eliminated them. The anti-tail could be a brief outgassing pulse. It could be a fragmentation event. It could be a viewing angle artifact revealing a dust sheet that's been there all along. Each interpretation fits part of the evidence. None is proven, and that open-endedness is not a flaw. It's the current state of knowledge, the edge where measurement meets inference, and where the next observation, if it comes, will either confirm one hypothesis or reveal that the question was more subtle than we thought.